Okay, so that is started.
Yeah, so I'll just send out the message on Moodle.
Yeah, I think I did something wrong. I mean, my message didn't go through. All the other messages went out, but this one I sent between those two messages for some reason go out.
Yeah, I'm just going to send the message with the link in there.
I thought you already sent, no?
No, I'm just typing it out right now.
No, but I got a mail about the Zoom link. Oh,
okay.
no, but that is only for joining.
Okay.
I have a message from you that you have joined. Okay.
Yeah, I've sent out a message on Moodle.
Yeah.
Okay, sure. So now I guess people will join in 10-15 minutes.
You don't have to admit. I mean, I've set it up such that
Mhm.
you can admit it. You can also record.
Yeah, I'll do that. I'll start recording.
Once they come.
Yeah,
Okay.
yeah, right.
I'll have to go by 7:30. Okay.
Yeah, I think I'll be done by then. So I hopefully won't take more than that. But you
Only
can.
thing is that the live stream has to be stopped first before the Zoom session is ended. Otherwise, sometimes the YouTube will not save. Okay.
I see.
So that's why I'll be around anyway. Okay. So even if I have to leave early, you can stop the explicit recording. Okay.
Right.
So that will be there as a backup.
Hmm.
I don't end the session. I'll come and end the session.
Okay, sure. Yeah.
And I will end the live stream, and after which I'll end the session.
Okay, sure.
Don't, please remember not to end the session.
No, I'll not end the session. I'll just leave.
The person that is not regularly attending is probably this guy, Hardik Kalra. I don't think I've seen him.
I don't think I've seen him either. At least not in the past 4 classes.
Yeah. So we have a Kauri Shauryam, Drubjyoti, Ghosh, Hardik Kalra, Nabeen Kumar Sahu, Ashutosh Maurya.
So Ashutosh Maurya, I think he's in classes, but I've not talked to him even once.
Yeah, he's there. I mean, Soham is there as well.
Soham is there.
Yeah.
Soham I had like a couple of conversations with as well. He's from a DS background.
Yeah, there are 3 people with DS background. Interesting, no?
Yeah.
Yeah. So they would have done all this basic machine learning, and maybe some of them even advanced machine learning, or they might be taking it simultaneously. There are 2 machine learning courses that are.
So I think, basic, like the first data mining machine learning, the basic machine learning course is a prereq of the advanced. And if I remember correctly, the advanced one is an even semester course. So I think people who are taking this course, if they have done anything, they would have probably done both those courses. So I'm sort of confident that most of the data science people are familiar with even advanced machine learning.
What are covered there? Okay. So neural network are covered where? They're covered in both.
Yeah, so basic machine learning, the last bit covers neural network because there's a lot of other machine learning algorithms, like more older algorithms that are covered before. And then in advanced machine learning, they cover various architectures of neural networks in detail. Like you'll have neural networks, you'll have convolutional neural networks. There are the recurrent neural networks. There are these things called GANs, transformers, even more complicated architectures, essentially, which they cover.
Reinforcement learning, etc., they cover in this advanced machine learning, is it?
Yeah, I'm not sure. I think reinforcement learning is a separate course in itself.
I see.
So reinforcement learning is one of the things which is kind of has its own set of challenges and separate things you have to take care of. So I think it's a separate course. KVSAT takes it.
Yeah, and also the mathematics is slightly different. No?
Yeah. And it's one of those things where with some simple situations, you can actually get some guarantees for convergence, like theoretical guarantees, which is very interesting. So that mathematical aspect is also covered there.
I'm wondering if indeed there are people, if we could kind of quickly educate ourselves about what kind of explainability and interpretability, if we could
Yeah. I think
into that. Yeah.
right. I think we can do something. We can set up something like a weekly discussion meeting where we read up something and then discuss. Right? That will be good.
Yeah.
In fact, that is one of these things that in TRDC there is a lot of there's at least in some of the junior people there's a good culture of setting these things up. So like there is a quantum computing group that is going on right now. Where so I think we can do that.
We can even ask if Madhukar.
I'll definitely ask Madhukar if he's into it, and then he'll know if somebody else would want to come. That is also an option, because the more people, the better it is for everyone. I believe up to a point, I guess.
Yeah, I mean, too big for these should not be. They won't be too big.
It won't be too big, yeah. But like 4 or 5 people is good, I guess. Yeah.
No, I was also seeing if we get somewhere, would it be? There are some simple ways to, if it's worth exploring, if some of that can be formalized as part of this course.
I think right now, I don't think we can change track. But like we can see, we can be open to that, but I'm not confident that we'll have enough time to do that. What I'm saying is that we'll have to sort of look at that and then find some slice and then rearrange other things in the course.
No, even if it's done, it will be towards the end.
Right. But I think if some of the people who are already attending this course, if they also want to come, and that way we can have a separate unofficial thing. But officially, like doing it before the end of the course, I'm not sure if we'll have time, but let's see.
But the other thing in the schedule that I thought was, simplex can be covered as a decision procedure. No. Okay, so the way that I cover simplex, of course, it can be covered as a standalone independent thing. But it's also covered in terms of the way I present it as some interfaces. We need to cover a little bit of DPLLT and how the DPLL interfaces with DPLL. Because the ReLUplex becomes more meaningful only if they contrast it with how it might work with DPLLT. Okay. Once you have simplex integrated with using the DPLL framework on top, I mean, you can use an SMT solver to do what ReLUplex does. But ReLUplex does a certain, at one level, you can view that as an optimization. It integrates some of those things that DPLL would do, pushes it down into the simplex. layer. Okay?
Right.
So, I don't know. I mean, but I guess simpler
Yeah, I think we can.
can be discussed even without that. But if I have to do it, then there will be 2 classes that will be required to discuss DPLL and DPLLT between simplex and reluplex.
Yeah, so we can I think yeah, so let's see. So then okay, I mean I think we can definitely make sense to discuss it. I'm just not sure if we'll have time at the end. The only thing I am sort of thinking about is that the people want, like I think it'll be good if they can get started on the project by the end of say this month, right? Because then yeah.
Yeah,
So
all the rest will be the same. Okay, Deepali, Lin, all that we'll discuss.
right, so we have around 8 classes. So if we can fit it in by the end of this month, I think we should do it. So I'll do something. I'll just add 2 more classes for DPLL into this existing thing and see what it comes to.
Okay?
Yeah. Because we'll have to have Deep Poly and Linsen on top of this Reluplex, right? So I guess DPLL 2 classes, Simplex, Reluplex, and then Deep Poly Linsen. So I think it might be doable. I'll just check. Okay, so it's time, but nobody has shown up yet. Hopefully the link did go out, right?
Classes, I mean, the normal time is people are 5 minutes late.
Yeah, that is fair.
Yeah, I think
but
maybe you could insist because the tutorial is optional. I think it would not be courteous on their part to indicate if they'll attend or not. That is something that they can request. No, I mean, we can request them to do.
Yeah, that is definitely makes sense. Because if nobody is interested in a particular thing,
yeah,
then we can skip it.
Doubts and so on, then you can skip it. And maybe certain things we may insist that, I mean, we can't insist, but then we could say we strongly encourage that they do it if they have doubts. Okay, things like that we can do.
Yeah.
But this is important enough that they should attend. Should have.
Yeah, I think that is hopefully communicated because one of them actually requested me to show the Python interface when I was covering the SMT interface last time. So I believe that there is interest in the sense that people would want to look at this. What I'm not sure is if they'll like join the Zoom link or not. That is the only thing I'm worried about.
Why would they not?
As in, if they didn't get the message and if they didn't look at the Moodle messages and
you just sent it as a email, no?
Right, as a Moodle message. So
why will they not look at the Moodle?
yeah. I mean, that's true. At least one person should, and then he'll probably let the others know. Yeah, but I think like anyways, they'll probably be here in not earlier than 6:40, given how it goes usually.
Is it too late for them? See, this is kind of an odd time. Okay.
Yeah, but
they must. I would like to have some snack and a cup of tea. Okay, but there is enough time, I think. I mean, at 5:30 they can have some tea and snacks, and then come here, and then before dinner. Okay, and of course, it's a long day. Then you want to unwind and relax.
Yeah.
Oh no, there are a few people now.
Yeah, I think people are coming in. Yeah, but like 6:30 is also like this night, like the evening canteen ends at 6:30 if I remember correctly. So we can't have it. Like it's no point having a tutorial that clashes with that time.
Oh, so the snack time there starts at 6:30 or closes?
Closes.
Yeah.
It closes, right? Dhruvajyoti, if I'm not.
Yeah.
Yeah.
Like the snack time closes at 6.
6, right? Yeah.
Wait,
Now it's 6:30.
Right. So that is what I also know.
What time do you guys go for dinner? When does the canteen open up for dinner? So we were just discussing if 6:30 is too late or it's a perfect time.
6:30 is fine. Because dinner opens at 7:45.
Hmm.
So if I remember correctly, dinner opens at I think 8.
So that has been preponed by 15 minutes.
Acha, I see.
Maybe you can start.
Yeah, so I'll just start. Yeah, I think
you may want to record.
Yeah. All right. So yeah, let me just share screen and then we will start. So I'll be going over the Python interface for Z3 and I'll do some, like I'll basically code and talk about the code. So I'll do some live coding. So that is how this thing will be arranged. Right. Okay, so by the way, about installing Z3, I think the easiest way to go about it is to actually install this particular thing. So if you go to PyPy, there is a wheel that will, if you install it, it actually gives you both the Z3 binary. So there's the command line utility and the Python interface. So if you search Z3-solver, yeah, so this is Z3 solver, SMT solver library, this one. So you can install this one and you can just install this via pip. This will work on all platforms, Windows, Linux, all of it, even macOS. So like, I think this might be the easiest way to do it. But depending upon your specific machine, there might be even easier ways. So, but like I'd say that like this is the most general easy way of installing Z3. Okay. So this is one thing.
Is this the Python API that you were talking about?
Yeah. This is the Python API.
Okay.
Yeah. So I'd say just install this, and then you'll get both Z3 and the Python API together. And if you have already installed Z3, even then you can just install this. I think that will also not be an issue.
So when you say you'll get Z3, you mean its file interface and the GUI interface, is it?
Yeah. Both of them will be here packaged here.
Okay.
Yeah. So I think it'll not get stored in your root directory as it's commonly done in Unix, because pip is not like pip doesn't take sudo access. So Z3 will probably be stored somewhere in home. But yeah, other than such details, which you can decide on system specific details, this is I think an easy way of installing it. Like if you install it like this, I don't think you'll have to worry about it too much, essentially. This is one thing, and there is 2 resources which I'll put on Moodle, which is really good. So one is this really nice tutorial for the Python interface. This is by a person named Eric Pony, and it is in his GitHub. It's got a lot of things here, and a lot of these things we'll probably not be needing. Like it's got fixed points, it's got even more advanced stuff. It shows you all the knobs that you can like change inside of Z3. But yeah, just the basics here, that is, already more than good enough for our purposes for now, at least. So you can go through this tutorial. I'll just increase the font. This is good. The only caveat is that this is actually written in Python 2.7. So for example, the print statement doesn't look like this in Python 3, right? And we'll be using Python 3. So you'll have to sort of translate from Python 2.7 to Python 3. But all the Z3 APIs that are being shown are all the same in both 2.7 and 3. Okay. So that is there. And of course, there is the reference, the namespace reference for Z3. This has got all the functions that are available and all the documentation for it. So you can go through that or refer to that whenever you are confused about some things, right? Okay, sure. So let's start. So first things first, let's import Z3. Right. Okay. Font size, is it okay?
Too small.
Wait, so I'll just do something. Is this okay now?
Yeah, it's
A
okay.
bit larger would help.
All right, sure. Wait a second. I'll just close this so that I get a little bit more space. Is this okay?
This is good.
Okay, sure. So let's import Z3 firstly. Now, if you remember in the SMT interface, what we were doing was we were basically building these expressions in SMT2 and then adding them as asserts to Z3, right? So that basic model remains the same. However, here what we need to do is we need to create this specific object which represents an instance of Z3 essentially, which is called solver. And you create that by just calling the Z3.solver constructor, right? So this solver represents an instance of Z3, and essentially you can have as many solvers as you want in your code. And each solver is basically going to behave like a separate independent instance of Z3, right? Okay. So now, if you remember, the SMT interface had sort of two steps. One was this declaration of variables. And then the second step was add your assertions, right? The similar thing we'll have over here. So declaration of variables is essentially done like this. You take, say, let's say that we are going to declare a variable of integer type. So you can say int, or sorry, z3.int. So this class represents an integer variable, or an integer constant inside Z3, right? And
There's
here,
a question, Diganta.
oh yeah.
Can you please tell? Yeah.
One second. Sorry, I can't seem to. I'll just drop the share so that I can look at the chat for a second.
And I've read it.
Okay.
Can you please tell?
Yeah. Sure. So the difference mainly is that the Z3 or the SMT interface that will basically take in some expressions in this specific language called this SMT2lib language, right? So the SMT2lib language, it's designed to be something general enough that it can work with any SMT solver. So Z3 is just one particular SMT solver which has been like designed and maintained by Microsoft.
Yeah, so SMTlib is just a format, a standardized format for writing formulas in the SMT logic, which we introduced in the last class. So it's just a standard input format for writing formula assertions, basically, and a few other things.
Yeah, and
but there are some differences, right? So some of the features doesn't work. Some features do not work for Z3 Pi.
Right. So in terms of features, I think actual solver features are common between both, but the key difference in terms of usability, if you will, is that if you're using the Python interface, since you already have like a proper programming language running, you can do things like do multiple queries, or check the result of a query and based on that decide if you're going to do another query or not, right? But with the SMT2lib interface, you can't do those things because the SMTlib2 doesn't allow you to do things like inspect the model that is being returned and based on that frame a query or something like that. Right?
Once doing that in Z3 Pi, some things are not working. I have seen.
I'm not sure if there is anything that is not working in Z3 Pi but works in SMTlib2. Sir, are you aware that there is?
No.
Yeah, I'm not sure, but have you faced such some issue like that where something in Z3 Pi?
Yeah, I can do the precise next day, but I do not have the example right now. For return values and all, I have seen things are not working there. Yeah.
I see. Okay.
I can give you example in case it's required next day.
No, that if there is something like that, then that would be, I think, an interesting thing to be like wary of, I guess. Right. So then that is something that we should always, I guess, be wary of. But I wasn't aware of that actually. So if you can you just send the examples? That will be something really interesting, I think.
Yeah. I mean, I don't know if they, for example, quantifiers. I guess quantifiers are, you could make quantifiers in both.
Yeah. So in terms of language features, I think both of them, like the SMT logic segmented Z3 targets, the interface also has that. But so is it something like a missing functionality, or is it more like some bug in the API? The example that you're talking about?
Yeah, I did it longer, but yeah, that time I found that there are some functionalities which are not there. I mean, but you have to give some precise example.
Okay.
Telling this.
Okay, sure. That'll be great if you can just like send the example of the functionality missing, because that might be the case. But yeah, I was not aware of that actually. Okay. So I guess I'll move on to talking about these variables. Right. Okay, so essentially you declare variables like this, right? The syntax for this is you call this constructor for Z3's representation of a constant, and you pass in whatever the name of the constant you want to put. And this name has some significance to it, actually. We'll talk about this in a second. And then what it returns you is it returns you something which is called a reference to an AST. So AST is basically a representation of a expression. So it returns an expression which then you can store in a variable. So this variable X is actually not like referring to the value of X or anything like that, but rather it is an expression which is the expression just X, right? So always when you get variables from, doing calls like this, like whatever you get returned inside Python from doing calls like this, remember that it is just some reference to an expression. Okay, it's not an actual value of a variable or anything. Like if you try to print x.expr, you'll not get the value of X. You'll rather, it'll print out the expression which just has X in. So let's just, see that, I guess. Okay. So I'll just run it here. Right, and you see it prints out X. So it prints out the actual expression and not the value or anything like that, right? Of course, right now we don't, the value, we haven't really defined what it would be, but even if you had some specific value, you can print out that value, to print out just X. Okay. So this is variable. So let's do another variable, right? And now we come to adding assertions. So adding assertions actually can be split into two steps in this particular interface. So you have 2A, which is building your expressions. So here what you can do is you can actually use your normal Python operators to manipulate, two expressions and then combine them to a larger expression. So for example, I can have an expression for xpy and store it into a variable by just saying xexpr plus yexpr, right? And then I can print that. So by xpy, I mean x plus y by y. See, and now it gives you two expressions. It gives you the expression x and it gives you the expression x plus y, right? So in this way, you can build expressions. And then finally, when you have some expressions, you can add them as assertions. So for example, let's build an expression xpy is greater than 0, let's say. So we can say xpy is greater than 0. And remember, these operators have some particular meaning in Python, but what has been done inside the Z3 API is that these operators have been overloaded so that when you actually are calling this, instead of some values being added, this is being interpreted rather as take this expression and combine those two expressions with a plus to get a different expression, right? So these are all of these manipulations or all of these things that is happening in these two statements are happening at the expression level. At no point here are we even talking about values or semantics.
So they are like you're building the terms that of the logic in the that are part of the formula.
Yes, exactly.
So like I defined in the class. Okay, so They're just syntax. Yeah.
Yeah, so that is exactly correct. You're just building the terms and in a syntactic way essentially via this interface.
And here you're introducing an atomic formula, XPY expression greater than 0.
Right. So let's again just print just to make sure that everything is same. So as you see now, we are printing out the actual expression that x plus y is greater than 0, right? So now we have an expression that is an actual atomic formula, right? So now this is an expression that is a formula in your logic, and so we can actually add this as an assertion, right? So let's do that. So the way you do that is by calling solver.add, and this will basically add an assertion to your solver. So if you remember, your solver can have as many assertions as you want, and then when you do a SAT check, the solver is going to essentially try and satisfy all of those expressions, right? Like come up with an assignment that satisfies all of those expressions simultaneously. So let's see.
It's as though it's a conjunction of all the assertions that you've added. So,
yeah, exactly. So it will be a conjunction. So we have this solver.add. So here we're basically adding this expression into the solver. And now, I mean, I can write it as a step 3, I guess. We can do the check sat call, right? So the way you do that is you do solver.check, and let's just print out the result of that. Right. So it's sat, and that is not surprising, of course. Like x plus y greater than 0 is a satisfiable formula, right? And let's see what the model the solver comes up with. And it, of course, assigns x equal to 1 and y equal to 0. Right? Okay. So now let's say add another expression. Let's say that x plus y is greater than 0. And let's add 2 more assertions here. So here, I'm going to just, instead of building the expression separately, I'm just going to build it inside of this add function itself. This is just a compact way of writing the code, right? So I can directly say something like, for example, x.exp is less than 0, right? So here I'm directly building the expression and then passing it to the solver in one line. So it's just, nothing special going on here at all. So again, I can do this. And again, it's sad, and this time it says x equal to -1, y equal to 2, and that is also okay. And now let's do the same thing for y, and it should say unsat, right? Yeah, it gives you an error. So firstly, up until the point where it says unsat, it's fine. But then we get an exception, right? And the exception is Z3 expression and exception, sorry, and the error message is that there is no current model, right? So of course, this is basically the same error that we were seeing before, where we were calling this get model sort of function. And but because the result of check sat was unsat, you don't have a model that it can return, so it's throwing you an error, right? But now we can actually write code to handle this case and avoid this error. So we can do this. We can say result is equal to this, and then we can say if result is z3.sat, I think it's sat, yeah. Then we'll print the model, else we'll just print no model. So again, if we run it, now we get to see that, okay, we can actually inspect the result of this and then based on that say that, there is no model, right? Okay, so is the code so far clear? It's basically directly like apart from this bit, which is something you couldn't do in this SMT2 interface. The rest of is directly a direct parallel to the SMT2 interface itself, right? So is it so far clear? Does anyone have any questions? No? Okay, sure. All right, so now let's look at something interesting. Okay, so we are going to delete this particular thing. And of course, if I now call it, it should be sat and it's giving me the same model. But let's change this. In YEXPR, let's change the name inside here to X. Okay. So now we are having XEXPR is the result of calling Z3 int.x. And then YEXPR is also the result of calling Z3 int.x. And then we're building the same X plus Y expression, and we're adding the two assertions. The X plus Y should be greater than 0 and X should be less than 0, right? Now, I'll run this, but before that, does somebody have any prediction? Will this give you a SAT or an unsat? Any guess? Or make one, somebody, at least one person make one guess. Hello. Hello. Am I audible?
Yeah, you're audible, but everybody else is muted. They don't want to speak.
Okay, fine.
Guys,
Somebody who has not seen Z3 interface before, just a guess. Is this are you finding this too complicated to follow what's going on?
so I mean, I think I can give them a hint. So what is, if you were to print XPY expression, what would it be?
Yeah. Like what would this particular print statement produce?
Unmute your, everybody's muted.
Or even before that, if I were to just print this, right? What would just this be?
Yeah.
Let's make it much simpler, I guess. Just give me the, what should this be?
You guys,
Why?
Yeah, you were saying?
Plus X.
Yeah, it'll be
Why?
just X.
right? X. Huh.
It'll be just X. See, because I mean, if it doesn't make sense, if I were to not even have this expression, then this is just some variable name inside Python. There is no Y in the picture at all, right? And since we're not using this, actually, when we're printing this, there's no Y in the picture. So essentially, this expression actually refers to an expression containing just the variable X, because we passed X as a name over it. So yeah, the person who predicted X is correct. The other person is not. Let's just run and make sure that I'm saying yes. See, it's just X. Right? So let's run comment this bit of the code as well and run it again.
So this is the point here that Digant is making is, don't get confused with the logical variable X with the program variable. That's all.
Yes.
Program variable XX per YX per that he has, they are just Python variables denoting symbolic expressions, which in this case are terms. And terms start with variables, logical variables. I mean, variables in the logic. That's what I mean by logical variables. And, that's what it is. Yes.
Yeah, exactly. So like this, although I've named it Y expression, this name is actually bad in this case, because what this Y expression contains is just a simple expression containing a single variable X, right? So then what we're saying when we are constructing this expression is that X plus X is greater than 0. Similarly, now if we add this assertion, what we're adding, the assertion that we're adding is that X plus X is greater than 0. And again, if we add this assertion, now the assertion that we're adding is X is less than 0, right? So then when we do the SAT call, what we're basically checking is X plus X is greater than 0 and X is less than 0. So it will be unsat, right? So this is something you can do with a solver. If you're like confused as to what's going on, you can actually print the solver directly, and this will print out all the expressions that you've added in so far. And see, the expressions are X plus X greater than 0 and X less than 0. So this is actually like a pitfall that you can, it's both something you can exploit and a pitfall that you can fall into, like a potential bug as well. That if you have two different variables in this scenario, and they're referring to internally the same Z3 variable or the same SMT variable, then, although you're probably thinking in your head that you're constructing the expression X plus Y, internally it's actually constructing X plus X, right? So these variable names that you pass inside here are actually really important. So, it should be kept distinct when you want distinct variables, and you can force it to be the same by passing it the same name, right? So the good thing about that is that if you have some canonical naming scheme for your variable for whatever problem that you're working with, then you can just, use this expression to unambiguously create a variable, right? So like z3.int x, no matter where you call it, is going to refer to the same variable. The bad thing is, of course, that this particular behavior can be counterintuitive in some situations. This is an example of a situation where it can be counterintuitive, and that might lead to bugs, right? So this is something you should know.
Why you want to call two things, store the same variable, logical variable in two things, but nonetheless, that's a different point. I mean, maybe there is.
Yeah, so so maybe if you want, you can actually write some really compact code like this, and there you can do this. For example, I can do z3.int. Instead of storing the variables anywhere at all, I can do z3.int x plus z3.int y. So I can write something like this, and then here I can then write z3.int x is less than 0, right? So then I don't need any of this code at all. And sometimes it might be very compact to write code in this way. It's basically what I had in mind when I was saying that.
Yeah. So you can be less verbose. You can store
Right.
it and you can use the same thing. Different. It's part of different terms.
Yeah, and essentially this z3.int x and this z3.int x, although there are two different calls, they're actually referring to the same variable intent.
Yeah.
That is the point that I want to make. Right. And of course, this will give you the expected answer. Okay. So far, is this all clear? Any questions? Somebody say no at least. Yes. Okay, fine.
No questions.
Sure. All right. So now let's do. Okay. So now I'm basically going to code up something a little bit more involved. Let's just code up the two ways of doing n queens that we saw, right? And we're going to actually be able to code them up in a much more succinct way, hopefully, and keep n general, because now we have like Python code that we can write to formulate our problem, right? So let's do the first version would be n queen, let's say Boolean, right? And here, what we're going to do is we're going to, so let's say that I'm going to take the number of queens as a command line argument. So, yeah. Now let's say that we want to actually encode this using the Boolean sort of encoding strategy that we thought of, right? So that is, we'll have n square variables, each variable representing whether a queen is sitting in a particular square or not, right? So let's declare our variables first. So let's neatly pack all of our variables into a 2D array. So let's say and we're going to say something.
Did you explain what sys.argv?
Yeah, so this is just going to, this is not a part of Z3. This is just going to be some code to read the command line argument when we call the script, and that will be the value of n that we want.
Oh, okay. Fine. So when you input things, yeah. Okay.
Yeah. I mean, okay, I think we can just ignore this and just put n to be something constant in the top of the file as well. That's it.
Okay. That was a Python thing. Okay, fine.
Yeah. And I forgot to import Z3, but that is something we need to do. Yeah, so now let's say that, let's again have some standard variable naming screen. So let's say that v, so we're going to say v plus, the row index and column index, right? So the way you do it would look something like this. So we have two blanks in the string, and you can fill it up with this string.format method. But if this code seems complicated, don't worry about it. This is just some Python code to generate this string that is going to represent the variable name, right? So, if this is something, if you're not familiar with, say, the format method for strings and such things, don't worry about it. It's basically just some Python code that is going to generate the string that we want as the variable name, right? And what it's going to generate it using is the two indices of the row and the column that we are on. So let's say right. So this will basically just create a 2D array for you. It's going to be filled with this z3.bool types. And it's going to basically be n by n large, right? So there's an inner loop which is filling each row, and then there's an outer loop which is going like one row at a time. And this is some compact Python way of doing it. So now we have these variables. So let's start adding our constraints, right?
Could you sort of show the output of how the Boolean variables will look like?
Yeah, sure. So let's do that.
Yeah.
So let's just print this thing first. Because maybe I'll just explain that bit of the thing as well. Oh, sorry, I was writing the wrong thing. Yeah, so if you look at it, it's v00 is the variable at row 0, column 0. v_0_1 is row 0, column 1, and so on, right?
Yeah.
Yeah. So and this is then one row. So from here to here is one row, and then the next row is like this. It's not printed very nicely because it's just directly printed, but it makes sense, right?
Yes.
Yeah, and what this is doing is it's going to just take I and fill this first hole given by this curly braces with it, and take j and then fill the second hole given by the curly braces with it. Right? So that is what the formal method essentially does. Die a JR or loop indices, right? Sure. Okay, so now let's add, say, the row constraints. So let's say. So before that, we should create a solver. Right. And now let's say in the row constraints, what we want to do is we want to go over each row. So R represents whichever row we are in now. And then we want to, let's do it basically the most straightforward way, right? So let's pick each possible pair of positions in this row. And let's say that those two positions can't both be true. So there can't be a queen in two positions along the same row, right? So let's say that so this is the two positions are going to be I and J. We're going to have a nested loop. And then inside that, we're going to say, we're going to ignore the case where I is equal to J. So we're only going to do things if I is not equal to J. And then inside that, we're going to just, add the particular constraint for that particular row, right? And now here, one of the operators that is actually not overloaded in Z3, or the class of operators that is not overloaded in Z3, are the logical operators. So for logical operators, you need to call Z3 functions and not and such things, right? So instead of, you can't just write not and then some expression, okay? Because not is something that is actually can't be overloaded in Python. So you have to instead do this Z3.not and then put in some expression, right? So here what we want to do, we want to say that Z3.not, like not the particular variable at the ith position and the jth position in the rth row is true, right? So let's say Z3.and, and then here we're going to say that boolvars row number R, column number I, row number R, column number J, right? So does this code make sense to everyone? We are saying that, okay, this bit of the expression says that, the variable at Ri and Rj is true. So that means there's a queen sitting at Ri and a queen sitting at Rj. That should not ever be the case. So we're adding a not, and then we're adding that as a constraint to the solver, right? And then since we're doing it inside this loop, we'll basically get it for all such Ri, Rj pairs, right? Does this make sense?
Yes.
Yeah. So like this, then we'll have this same sort of code.
In other words, what you're doing here is kind of constructing a conjunction of a big conjunction of a whole bunch of
Yeah, a whole bunch of these expressions saying that, you know,
negation,
two
yeah,
queens.
whole bunch of negation of these.
Right. So yeah, as you can imagine, the actual expression that is getting added into the solver at the end, or the list of expressions, is going to be a huge list of expressions here, right? I guess each expression is not that complicated, but there is a huge list that is going on. So ultimately, the query that the solver is solving is going to be huge conjunction of these many expressions. So let's duplicate this code and just, you know, do this. It's basically same for the column constraints, just the indexes will switch around, right? So here, let's
You can do for j in range I plus 1 to n.
For j in range I plus 1 to n. Exactly, yeah, that makes sense. And then we can get rid of this. That is nice. Oh, sure. So now here we're going to say it's going to be basically IC and JC, right? So then the row constraints and the column constraints are done.
Wait a minute, but then you have to replace J by C.
No, I'm saying it'll be.
What is C here?
So C is whichever column we are in. So this outermost loop is going over the columns, and then here I and J is going over each position.
Okay, good.
Yeah. So now we come to say the diagonal that is going to go. Basically, diagonals parallel to the primary diagonals. So let's call them primary diagonals. Right. So diagonals are a little bit more complicated in terms of the indexing and such, but I think it should be okay. So, okay. So let's do it this way. How do we index this? So we are going to again, so let's say that we're going to have two sets of loops, one for diagonals starting from the top and one for diagonals starting from the side, right? So, okay, actually, you know what, guys, with your permission, can I write this whole thing in a much more simpler way? So let's do it this way instead. So let's just go R in range n, C in range n. And then inside here, we're just going to add all of the constraints based on what the various things in R and C are, right? So firstly, so it's okay. So what I'm basically going to do is delete all of this and then instead add constraints based on what the two positions are. So and this horrible thing we have. So firstly, if you're looking at the same cell, then so basically what we're doing is we're looping over two cells. So R1C1 is one cell and then R2C2 is another cell. And then if cells the same, then we skip. So that we'll do essentially by saying R1 is C1 and R2 is, sorry, R1 is R2 and C1 is C2, then we're just going to continue. We're not going to do anything in that iteration. Otherwise, let's say that these two cells are in the same row, right? So what does that mean? That means that R1 is R2, then we're going to add a constraint, right? same constraint as before. So we're going to say okay. So does this make sense? So this code will already handle adding the row constraints, right? This makes sense to everyone, right? I hopefully didn't like confuse you guys too much with this. Hello.
No.
Yeah, sure. Okay. So then again for columns, we're just going to say right, and then for diagonals we can say so if R1 minus C1, so absolute value of that, right, is equal to the absolute value of R1 minus R2. Then we are, the two cells are diagonally separated from each other, right? This makes sense, right? Am I correct actually? But here, somebody say yes or no. Like, do you think this is correct as a characterization of the diagonals? Absolute value of R1 minus R2 and absolute value of C1 minus C2 should be the same.
Shouldn't C1 and C2 be actually R2 and R3?
Why do you say R2 and R3? I don't think I have R2 and R3 in the as variables. So the variables are R1, C1, R2, C2, right? Where?
Sorry.
Yeah.
I wasn't on this space. Sorry.
Right. So this makes sense, right? Okay. Somebody say yes at least or something.
Yeah, I think I don't know. I mean, sometimes it will be. This is just an implementation. I mean, if you draw these logical formulas first on paper, with
Definitely.
a big wedge and big thing that shows the conjunction. This is just an implementation of generating those formulas. Correct?
Yeah.
But I don't know if you had it. I mean, I think I have it in a slide. Those big formulas. Okay.
Yeah, I did talk about it. I think even in the last one.
You did. Okay, you showed that big wedge and big.
Yeah.
Okay, so these are just those things. Yeah, if they've already seen it, then they should understand it. Yeah. Anyway, I have to leave in a couple of minutes. Diganta, you continue. Okay,
Sure.
What you want to do. Depending upon how much this thing is, and then you don't terminate the session. That's all. Yeah.
Yeah. Sure. I'll just stop the recording and leave. I'll not terminate the session.
Yes.
Sure. Okay, so all that this code is doing, it's somehow programmatically generating all the constraints that you want to. Previously, we had to write it out manually in our SMT2 file, and instead now we are programmatically generating all of these constraints. So it's clear, right? And I mean, I have not made a mistake in the bookkeeping in this particular case, right?
It seems fine.
It seems fine, right? Yeah, sure. Maybe there is a bug, but let's see. I don't think so, though. So in any case, let's just now call the solver. So let's print out what it says. Okay. So just before doing n equal to 8, let's do n equal to 6, maybe. I don't know how long Z3 will take on this particular thing. Right, it says SAT and it's pretty fast. So let me just delete this one. Yeah, it's very quickly saying SAT, right? And let's just print out the model. And let's print out the model. And let's see. Right, so it's found a solution, it prints out this entire thing, right? Now there is the issue. Can somebody point out the issue?
Everything's false.
Everything is false. Why is everything false? We had to add some
You
more.
haven't mentioned that there are 8 queens.
Right. We haven't mentioned that there should be at least 10 queens, right? Yeah. So how do we do that? How do we now generate this constraint that there should at least be 8 or n queens? I'm going to make it a little bit simpler than just saying that there is exactly n of these variables are going to be true. Instead, what I'm going to say is that there should at least be 1 queen in each row, right? Is that okay?
Isn't that the same problem?
Isn't?
Like, you can't have more than 1 queen on 1 row because that will violate the conditions that you made earlier.
Right, but we also can't have less than 1 queen. So that will basically ensure that we'll have at least 10 queens, right?
Yeah, so like if we write a conjunction of disjunctions, then we're fine.
Right, so what exactly would be the conjunction of disjunctions that you want to write?
The conjunction is that for each row, conjunction is over the rows, and disjunction is over the cells of each row. That this
yeah, and the disjunction, yeah, exactly. And then the disjunction is saying that, okay, so each term in the conjunction says that, okay, something in this particular row has to be true, which means there's a queen sitting somewhere in this row, right?
Yeah.
Yeah, sure. So let's do that then. So now actually it's like I've been adding these small formulas into the solver, but there is another equivalent. Okay, so another theoretical equivalent way of doing it. Performance wise, those two ways might turn out to be different because of the internals of the solver. But another theoretical equivalent way would be to actually create a huge expression, right? So instead of adding it to the solver, we might have actually kept around a variable where we accumulate the expression by doing z3.and over and over again, right? So let's maybe do it that way. So let's explicitly make a conjunction of disjunction. So let's say disjunction. So this will be an array where each element is going to be one disjunction. And so let's say this is the conjunction where each element is basically one disjunction. Right, and then what we'll do is we'll go over each row, right? And inside there again, let's accumulate all the terms that we need to disjunct together into another particular list. So let's say terms. Then we can actually construct this list directly, right? Because what we know is that this should be one particular, so essentially it should be something like this, right? Right, make sense?
Yeah.
Right, so now what do we want to append? We want to append basically the disjunction of all of these terms. So let's do that. We can do that by calling z3.or, and then we can pass the terms, right? But if you look at it, z3.or actually expects, it's a variadic function which expects one term for each argument, right? So if you look at, z3.and as an example, or also operates exactly the same way. It's not like taking in a list of arguments. Rather, it's taking in this, like as many arguments as you need to pass it, right? So you can't directly pass terms. You have to pass star terms. What that does is that will basically convert this list to a tuple of arguments. So instead of passing the list terms to OR, we're rather passing each item in terms as a separate argument to OR, right? So OR now is going to see as many arguments as there are in the terms, and the arguments it's going to see are each one of the elements of terms. So this is just another some Python thing. There's nothing to do with Z3, but Python has this particular way of handling variadic arguments and functions and so on. So is this sort of clear what's going on here?
Yes.
Yeah. So now this at the end of the loop, disjunctions, this variable has got a bunch of expressions in it, and we want to do an AND over all of them, right? So let's say expr is going to be, or let's just do directly solver.add. And what we're going to do is z3.and. And again, we have a list of expressions we want to AND together. So we are just going to do star disjs, right? And of course, with you can, with the compactness of Python, you probably could have written this entire 5 lines in a single line. I mean, like z3.and, and inside there you push in again z3.or, and inside this and do some list comprehension and so on. But is this code okay?
Yeah.
Right, sure. So now let's actually call this thing and see what we get. Yeah, so now it still says sat, but some of these things are actually true now, right? Okay, so let's do something. Let's do a nice pretty printer for this model that we actually have, right? Because this, just looking at which variable is true and all, you can't really see what the solution is, right? So let's do instead some pretty printing. So again, we're going to go over all of the rows and columns. And then for each ij, we want to, now what we want to do is we want to query this model, and we want to actually find the value of the variable that has been assigned to in this model, right? So there is basically 2 ways of doing it. One is that you can actually treat the model as some dict-like object and then pass in the variable, but that has got certain caveats. It can throw errors in certain situations. The other sort of more robust way of doing it is doing model.evaluate, right? And then inside evaluate, you can pass in any expression, and it will basically evaluate the value of that expression inside the model. So you can pass in any expression involving all of these variables that you have, and it will give you back the actual value of that expression in that model, right? So here we are going to just pass in the expression, which is going to be just the value, just the variable r comma, sorry, let's make this c, just the expression vr comma c basically. And then, we're going to print either a space or an x based on what this particular value is, right? So we're going to print an x if this is true, else we're going to print a space. Okay. And let's not end the line after the print statement. So this, if you're not aware, this is basically is going to force Python to not go into the next line after the print statement is done. And then, of course, at the end of each row, we do want to make a new line. So let's just print nothing. Okay. So this is going to be some pretty printing. Is this clear? Let's see if it works at all. Yeah. So is this clear?
Can you use dots instead of spaces? Like just
Sure.
just
that
a
makes
small
sense.
game.
Just a small?
Nothing.
I am okay, sure. Yeah. Yeah, it is basically yeah, it's basically going to do some pretty printing like this. I just found this particular solution, right? So this is good. Now let's increase the value of n to, let's say, 8, because that is better. See, if you notice, it took some more time, right? So let's actually time this thing. Let's import time. And if I remember correctly, it's time.time, I think, right? So we're just going to measure the time before and after this call, and then let's just print out that thing. If I remember it correctly, it's in seconds only. So yeah, so it took something like 0.1 seconds, and with 6, it was probably something less than that. So let's just see. Yeah, with 6, it was like, so it's going from 0.10 to 0.12, right? So just to make this a little less tedious, I'm going to add that argument reading code back in. Right, and then we can just do it this way. So we did this, the first one was 8, the second one was 6. So let's try 10. So it's taking 0.02 now. Let's try 12. 0.4. Let's try 14. 0.6. Let's try 16. Almost 0.1 seconds. Let's just try 20. Let's try. I think a good amount of time is also being spent actually going through all of these loops and constructing these. But let's see what that happens to the Z3 call time, which is the thing they want to point out here essentially. Let's try 25. And okay, so you see now from 20 to 25, it almost doubled. So let's see what happens with 30. Yeah, so it's going to take some time. Now it's actually taking 1.7 seconds, right? So I'm not sure if I should dare try 35. Let's see if it even returns. But if you look at the trend, or at least that's, I don't know if the trend is very visible, but what I want to say is basically this trend is going to be exponential. The worst case, runtime of any of these SMT SAT algorithms, all of these things are always exponential. So no matter what you do, you're going to actually end up with an exponential sort of runtime, right? So like that's the worst case that you have to expect at any point. And say it's okay, it's actually, so interestingly enough, this was actually less, right? So while the worst case is exponential, there might be, some smart heuristics that actually give you an answer very quickly for even a large number of variables. So basically the sort of regarding performance of Z3, what I want to say is it's kind of erratic and hard to predict how exactly Z3 will perform in a particular given problem, because it depends on how you phrase the problem. It depends on how many variables there are, exactly how you're phrasing these expressions. You can maybe phrase it in equivalent but different way and get much better performance. That can happen. And why that happens basically depends on the internal heuristics of Z3, right? So basically there are various choices you can make at various points in these algorithms, and most algorithms will follow some heuristics for these choices. And then based on these heuristics, they, certain queries will solve very fast, while certain queries might take a lot of time. So for example, in the hardware verification sort of community, there people regularly use millions of variables in a Z3 call. And it actually returns fairly quickly as well. Whereas with programs, you can have very, few variables, but complicated enough formulae where people don't really expect Z3 to be able to solve that at all. What we find is that with neural networks, Z3 actually performs quite poorly, but you'll get to see that in an assignment hopefully very soon. So yeah, so at least is using Z3 so far, is it everything clear? And it's 7:30, so officially I'm supposed to stop, but just going to ask, like, is say 10 more minutes okay with everyone or not? Like if there's even one person who is not okay with it, we'll just do it some other time.
Yeah, no problem.
Everyone?
Yeah, no problem.
Okay. So I think there was Rohan and Nabeen. Dhrubajyoti, if you're in the library, you can also type.
No, it's fine. Today I am not in the library.
Right. Is it okay with you? Is it okay with you, Nabin? Oh, you actually were able to make Zoom, yeah? Nice.
Yeah, it's okay for me.
It's okay. Thanks. I'll not take more than 10 minutes. Okay, fine. I'll just make it quick. I think asking everyone individually is itself taking a lot of time. Yeah. So, basically what I want to show next is let's firstly just write this as a function. And this will take in the model. Let's say M, and we'll do the pretty printing for us, right? So, okay. So the reason why I wanted to do that is basically I'm going to now call this particular function many different times. So now this code actually produces one solution, right? But what if I wanted to produce, say, k distinct solutions, right? How will I do that? Anybody has any ideas? Okay, so the way you do that essentially by the way you enumerate models using SAT or SMT solvers is essentially by doing blocking out the particular model that you've got and then doing the query again, right? So what we can do is we can construct an expression that looks like this. We call it the blocking expression. And what that does is that will add a query to your solver or add a constraint to your solver, sorry, which says that, okay, this particular variable's values, the one that I've got in this particular model, I should not get that again. So the variables can be anything, but it should not be this particular combination, right? So basically that is going to look like some query like this. I'm just going to write it out in this sort of a way. So it's going to be a conjunction of all of the variables, go over all of the variables, look at the value in the current model and say that, okay, the variable's value should be different from like the one that I have in this model, right? So at least one variable's value should differ from the one that I've gotten in the model. So it's going to be an OR, and the OR is going to be over all the variables. And each term is going to be that this particular variable's value should be different from the one that I got in the model, right? So then what we're saying is that, you know, whenever you give me a new model, make sure that the variables values are actually different, right? Does this make sense? So let me just type it out. I don't think I have too much time, but any queries, please do stop me. So it's going to be, you know, again, we're going to have another z3.all because it's an array of arrays. I think that will be the easiest way to write it. So let's say boolvars are, and then we're going to do so this particular variable should not be equal to its value in the model, right? So if the value in the model was actually true, then we should say that this variable should be false, right? So if the value in the model is actually true, then we should say that this variable should be false. So we do c3.not of this variable. Just go to the next line. Otherwise, we're just going to put this same variable in again, right? So what we're saying here is essentially that look at the model for each RC. So we do this for C in range N. And then over here again for R in range N, right? So we're basically going over all the variables, getting the value from the model. And if the value from the model is true, then we set the, we basically create a term saying that the value of the variable should be false. Otherwise, we say that the value variable should be true, right? So what basically each one of these terms in this particular line says that the value of the variable should be different from whatever it is in the model. And then we're saying OR of all of this, right? So at least one variable should have a different value from whatever the combination that we got in the model, right? So let's do, now let's add this thing as an expression. Sorry. Right? And so this, now that you've added this as an expression, now if you do solver.check again, then what you will get is basically going to be another, if there is such an assignment, it's going to be another assignment of all of your constraints, but different one from whatever assignment you've gotten before, right? So let's put this entire thing in a loop. Right. And let's copy all of this code. Okay, so inside a loop, we're going to call the solver. And then if the result is SAT, we have found the solution and so on. Yeah. Nice. But then capital G is also go to the bottom, no? So that is also nice. Anyway, we can talk about theme configuration later. Yeah, so we do some call and then we check if it is SAT. If it's SAT, then we want to print the solution, right? And so let's just do this. And otherwise, we say that and then we break, right? So hopefully this code works. It's not too. Let's do say 6 and let's go for 8 solutions. Oh, I need to probably. Yeah. So it found 3 solutions and then it ran out of solutions. So now you have proven that these are the only 3 ways you can do 6 queens. Right? Let's see what happens with 8. How many solutions are there? This found 8 solutions. Okay, now it ran out of solutions. There are exactly 91 ways you can solve 8 queens. Isn't that interesting? So yeah, so basically this is the code, and I think I'll not hold you guys back. There are some more things that I wanted to discuss, but let me just ask this. We are doing this using the SAT solver, right? But we saw different encoding using integers. Can you do that? Like after seeing this code, does everyone feel confident that they can do that? So if I give this as an unofficial exercise, will you guys do it?
Exercise, what's the exercise?
So this is the code that uses bools, right? But last time when we were looking at the SMT file, we saw an alternative way of doing the same thing, but using integer variables, like where we say that we have one integer variable for each row, and it says that the integer variable represents the position of the queen in that particular row, if you remember, right? In the last tutorial.
Okay.
So can you do that? Like, can you do that encoding as well?
I'll try.
Yes, like, does it make sense? Like, as in, or at least is the interface and the API and all of that clear?
Yeah.
Yeah, sure. So there is another particular feature in this API that I wanted to show today, but I couldn't. But I think we'll do that some point later. It's already 7:40, so I'm not like hold you guys back for too long. Okay, so any questions? Yeah.
Yeah, I have a question. Like when I am finding a new solution, how am I checking that it's not matching with any of the previous solutions? Could you just go to that part?
Yeah. So see, okay, so let's do this. I don't think adding all of these assertions is a good idea, but let's basically do this. So let's print out the solvers in each particular iteration, right? So let's just do that some sort of debug printing here. Then we'll be clear. So now let's say we're looking at 6 queens and 8, right? Okay, or let's do 3. I think is better. Yeah. So the first solver is something like this, right? And it's going to have some huge number of expressions. And then we found a solution, right? And then what we're doing is we're adding the constraints saying that, like, the next, whatever solution now you give me, whatever the value of these variables are, they shouldn't be exactly the same as whatever values we got previously, right? So, okay, so it should just ... It doesn't show the entire thing. But I'll just explain it in math, I guess. But that constraint, that this blocking expression, it's going to stay even in the next iteration of the loop, right? So right now, before the first iteration, all the constraints that you have is basically just the encoding constraint, right? Then you add the blocking constraint and it blocks out this one particular solution that you got, like one particular model that you got in the first iteration.
Okay.
And then you go into the second iteration. Now your constraints are n-queen encoding and should not be this particular solution. So you get another solution. Now you again add that as a blocking constraint. So remember, you're not removing anything from the solver, right? So now your solver has got 3 sets of constraints. One saying that it should be a solution of n queens, and then 2 sets of constraints blocking out the 2 of the previous solutions that you got, right? So just accumulating these blocking constraints into the solver. So that way you're getting, the constraints for the previous ones as well. Is that clear?
Yes.
Yeah,
Thanks.
sure. Yeah. So the part of this thing that I wanted to show, but I don't think I have time, is basically how you actually can remove constraint from the solver. That is something somewhat complicated. The interface for that. You can do solver.reset, that will clear the solver of all constraints. But if you want to tactfully keep and remove certain sets of constraints, then you have to do something more. So I'll not be able to show that now, I think. So any more questions?
No.
Okay, sure. So if no one has any questions, then this is it. So I'll stop sharing and I'll stop the recording. But the live stream, sir has to stop. So he'll do that. Let's all leave the meeting, but let's not terminate. Right. So that's how we do. Okay. Sure.
Thanks. Bye.
Bye.